There is a clock on your oven that you have never set. Not the one that blinks after a power cut. The one that keeps time afterwards quietly for years, without a battery and without ever drifting. Nobody wins it. Nobody corrects it. That clock is not really a clock. It is a counter. It sits on the mains and it counts the rhythm coming down. The wire, a rhythm that repeats 50 times every second. All day, every day, across an entire continent. And in January 2018, that clock started running late. Not by a second. By nearly 6 minutes. Ovens, microwaves, and alarm clocks across most of Europe fell behind together, all by the same amount, over a period of weeks. Nothing was broken. Every one of them was working perfectly. So what were they measuring? The answer changes what you think about electricity, about the machines that guard it, and about how much time you actually have when it starts to go wrong. Start with the thing the clock is counting. The electricity in your wall is not a stream of stuff. It is an oscillation. The voltage swings positive, then negative, then positive again. And in Europe, it does that 50 times a second. In North America, 60. That number is called the frequency, and it is not a design detail. It is the single most important number in the entire system. Because frequency is what supply and demand look like when you turn them into a physical quantity. Every generator on the network is a spinning mass, a turbine and a rotor, sometimes hundreds of tons of steel, turning in step with every other spinning mass on the same grid. When you switch something on, you take energy out. The spinning slows very slightly. When there is more generation than demand, it speeds up. So the frequency is a reading. Above 50, there is too much power. Below 50, not enough. And because every machine on the grid is mechanically locked to every other one, that reading is the same in Lisbon as it is in Warsaw. One number shared by every country on the same synchronized network. Here is what makes that terrifying rather than elegant. There is no reservoir of electricity sitting behind it. What you use is being made at that instant somewhere you have never been. The system does not run on a buffer that drains slowly while somebody notices. It runs on a balance that has to be true continuously. And the tolerance is narrow. The European network is held at 50 hertz, with primary control working to keep it between 49.8 and 50.2. In Britain, the statutory limits are half a hertz either side. Go far outside that an equipment starts disconnecting itself to survive, and below 47.5. The system is in territory. It is designed to abandon rather than defend. So the whole thing is a wire stretched across a continent, held at a single tension by machines that never stop turning. And somebody has to keep it there while a continent does whatever it feels like. Which brings us to a mountain in Wales. In 1984, Britain finished a power station that does not really generate electricity. It has no fuel. Over a year, it consumes more energy than it produces. On paper, it is a loss. It was hollowed out of the inside of a Lydir Fawr, a mountain in Snowdonia. A main cavern 51 meters tall, 180 long. The engineers who built it call it the concert hall. And you could stand a cathedral inside it. 10 years of work. £425 million in 1980s money. Inside are 6 reversible turbines, 300 megawatts each. Reversible because that is the trick. When the country has spare power at 4 in the morning, they run backwards and pump water uphill, from a lower lake into a reservoir near the summit. When the country needs power, they let it fall back down. 9.1 gigawatt-hours of energy, stored as water sitting higher than it was before. But the storage is not the clever part. The clever part is how it waits. Because a turbine takes time to start. Water has mass, the machines have inertia, and if you need the power in seconds, a cold start is far too slow. So Norway does something strange. It keeps its turbines spinning at full speed in air. Compressed air is blown into the chamber to push the water out and away from the blades. So the wheel turns in an empty space, drawing barely any power at full working speed. 450 tons of machinery, synchronized to the grid, spinning in a dry hole in the dark, doing nothing whatsoever. Then the demand arrives. The air is dumped. The water comes back in. 0 to 1800 megawatts in about 16 seconds. Now, why would a country build that inside a mountain? Because of moments like the 4th of July, 1990. England were playing West Germany in a World Cup semi-final. It went to penalties. And when it ended, the demand on the British grid jumped by 2,800 megawatts, the largest television pickup ever recorded. To put that in a shape you can hold, one power company worked out that this is roughly 1.1 million kettles switched on at once. That figure is their arithmetic, not a measurement, but the 2,800 megawatts is real. And it arrived in the time it takes a nation to stand up. It is not a one-off. The Thorn Birds finale in 1984, 2,600 megawatts. Who shot Phil Mitchell in 2001, 2,290. England against Brazil in 2002, 2,570. Charles and Diana's wedding, 1981, 1,800. The grid knows the television schedule. Somebody sits and watches the program, and when the credits start to roll, a mountain in Wales gets ready. So that is the defense. Enormous, expensive, and fast. Now here is what it looks like when the defense loses slowly. Go back to your oven clock. It counts cycles, 50 of them to a second, 3,000 to a minute. That is why it never drifts. As long as the grid delivers exactly 50 hertz on average, the count and the time agree forever. Which means the grid has to be right not just now, but cumulatively. Every cycle it fails to deliver is a cycle your clock never counts. In mid-January 2018, the continental European system began running slightly below its 50 Hz average and stayed there. Not a fault, not a failure. A persistent, tiny deficit sustained for weeks. The cause was a dispute between Serbia and Kosovo, a political argument about who was responsible for balancing a control area. While it went unresolved, that area drew more than it put back, continuously. And the whole synchronized continent carried the shortfall in its frequency. The missing energy came to 113 gigawatt hours. And every main synced clock in most of Europe fell behind. By early March, they were close to 6 minutes slow. Sit with the shape of that. A disagreement in the Balkans about paperwork made ovens late in Portugal. Not by breaking anything, by very slightly slowing down the rotation of every generator between them. The European network operators said it plainly. This had never happened in any similar way in the continental European system. Nobody lost power. Nobody noticed for weeks. The only instrument sensitive enough to reveal it in most homes was the clock on the cooker. That is what a slow breach looks like. Now the fast one. Friday, the 9th of August, 2019. 16:52 and 33 seconds. Lightning strikes a 400 kilovolt line between Eton Socken and Wymondley in eastern England. The protection systems clear the fault in 80 milliseconds. The report afterwards is careful to say, this is not unusual. Lines get struck. The system handled it. But in that fraction of a second, other things let go. About 150 megawatts of small, distributed generation tripped off on a protection setting. Then the voltage control system at Hornsea 1, an offshore wind farm, did not respond as expected and became unstable. It fell from 799 megawatts to 62. A loss of 737. Moments later, the steam unit at Little Barford Power Station, 244 megawatts, disconnected itself. Its speed sensors disagreed with each other, and the automatic system shut it down rather than risk it. Total loss, more than 1,130 megawatts in about 1 second. The frequency fell, and when it dropped below 48.8 hertz, an automatic scheme did what it exists to do. It began cutting customers off deliberately to save the rest. 892 megawatts of demand was disconnected across the local networks. 1.15 million customers went dark. 2 hospitals, several water pumping stations, Newcastle Airport, a number of London Underground stations. And then comes the detail that I cannot stop thinking about. The system shed 892 megawatts of demand, but the transmission network only saw 350 megawatts of relief. Because sitting behind that disconnected demand was more generation, small and local and invisible from the control room. Around 550 megawatts of it went off with the customers it was feeding. The grid cut into its own rescue. In saving itself, it threw away most of what it had just gained. The regulator's language on this is unusually blunt. The reasons for this need to be better understood. It worked anyway. Frequency was back above 48.8 within 200 milliseconds. Back to 50 hertz within 5 minutes. Every supply restored within 45. But look at the clock on that. 1 second to lose the generation. 200 milliseconds to arrest the fall. The entire event, from a lightning strike to a million homes in darkness, took less time than it takes to read this sentence. Which raises the question the whole system now turns on: what bought those seconds? Not a decision. Nobody decided anything in that window. What held the line was physics, the sheer rotating mass of every synchronized generator on the network, slowing down, giving up its kinetic energy to the grid. That property is called inertia, and it is the only thing operating at that timescale. It does not generate power. It buys time, a window of a few seconds, where the frequency falls slowly enough for the controls to catch it. The British system operator says it plainly: the kinetic energy stored in these spinning parts is our system inertia. And here is the problem sitting at the end of all this. Wind turbines and solar panels connect through power electronics. They are not mechanically locked to the grid's rotation the way a steam turbine is. They can be superb at delivering power, and they do not, by their nature, contribute that spinning mass. So as the machines that made inertia as a byproduct are retired, the window gets shorter. The frequency falls faster. The controls have less time to act. Britain's response tells you how seriously this is taken. The system operator has begun buying inertia as a product in its own right, over £300 million of contracts, for 12.5 gigavolt-ampere-seconds of it. That is roughly the rotating mass of 5 coal stations, procured from machines that will spin without generating a single unit of electricity for anyone. We are now paying for heavy things to turn. Not for the power, for the delay. We call all of this the grid, and we treat it like plumbing, something that either works or is broken. But it is not plumbing. It is a balance held in real time across a continent, with no reserve behind it, defended by spinning steel and a few seconds of borrowed time. And it tells you when it is struggling. Not with an alarm, with arithmetic, which brings you back to the clock on your oven. It is still counting. 50 cycles a second, 3,000 a minute, and it has no idea what any of them cost. Somewhere a lake is being pumped uphill in the dark. Somewhere a 450-ton rotor is spinning in an empty chamber, waiting for a football match to end. If that clock is right, they are all still winning. And if it is ever wrong, it will not be because the clock is broken.